Welcome to SanfordFlipMath. This is AP Calculus. We are working through the Finney, Demana, Kennedy book for AP Calc AB, and we are in the third installment for finding volumes, part of the applications of integration section or chapter or whatever. And we're going to talk about the shell method. The shell method is actually a method that doesn't have to be used exclusively in most cases, but sometimes it just lends itself. Before I go there, I just want to point out to you there is a website that is mathdemos.org/mathdemos, and you can find a lot of things illustrated there. This has to do with illustrating the disk method or the shell method, depending on what's going on. And I just want to kind of take a quick peek at the shell method using this site. And the shell method uses a different approach. The disk method had to do with looking at a cross section that was circular specifically and adding those up and kind of looking like you're looking at little flat cylinders. And the shell method actually has to do with kind of peeling. It's like if you take a soup can and peel the label off or something like that and then roll it out. So shell method, I'm going to play a little animation for you. And the idea here is that each shell is like you wrap it around, or you could wrap it around again and again and again. So this is half shells that you see drawing here. And this is again from mathdemos.org. And it's just a different way, no, this is filling in the other half. It's a different way of setting things up, and it can be helpful. And again, it's not perfect, but it's kind of cool in the way it works. And sometimes it's easier to use than others. It really just depends on what you actually have going here. Okay, I'm going to play this one too, and we'll just see how it looks. Okay, so again, that's one shell. So this is, the idea here is there's a hole in the middle, so you're going from like maybe this x value to this x value, and these are all little dx's. So this video is going to exclusively look at shell method and you know, try and look at, you know, how do we apply that. Okay, so what I need to talk about first with this is, again, that idea of, you know, how does it actually work? And these are still shots from the idea of the shell method. And so sometimes all we're talking about is a simple equation. And again, the idea is that these are little dx's, and we make a three-dimensional object out of this by spinning around, in this case, around the y-axis, and you can do this around the x-axis also. These just all happen to be oriented around the y-axis. And here's the idea. If I take some kind of a can, okay, so it's a Campbell's soup can, chicken noodle, whatever. If I take the label off of it, okay, so I you know, remember when you used to collect soup labels? Yeah, I don't do that anymore either. Okay, and if I unroll that label, then the label is going to roll out like this. Now, the question first question I have is, how long is that label going to be? Well, whatever the circumference is, okay, that's how long it's going to be. And then the height of whatever that can is or shell is, that's going to be the height of that label. Okay. Well, circumference you already know is 2 pi r. So whatever that radius is, the circumference is 2 pi r. That's the circumference, and then the height is well, it depends on what the function is. And then the other issue is this shell has a thickness. Well, that thickness is well, in this case it's dx. It's also the change in radius, dr. And if I lay this flat, and this had some thickness, so I unroll it and it has some thickness, well, that depth, that thickness is dr. Okay, so the cool thing about this is that I can find the volume this way also, and what I do is I do circumference times the height times the thickness, and that's going to give me a volume. Well, that's the volume for one of those rolled out, and as you've probably guessed, we're going to add them up. So this is called the shell method. Now, there are much more in-depth, longer discussions of this, but that's the short version. Okay. Well, what I'd like to do is take an example that we already did. Now, this was in the disk method. It was from the last video, and we took slices. Okay, so here's a slice, and we did basically pi r squared h, and that h in this case was the thickness of that slice. So this was dx, and this is the area of that base, and the radius had to do with the equation. Okay. Well, I want to do that again, that same exact problem again, and what we're going to do instead is the shell method. Okay, so let me draw it. Okay, and again, we're looking at y equals x squared, or the square root of x, excuse me. So 4, so this is at 4, 2, and it says rotating around the x-axis. Okay, so if I spin this, think of this like an axle, like on a car or whatever. And if I spin this, it makes a circular shape outline here. Okay, and same here all the way. So it's going to be an upside down version of that same function. Okay, and then the idea is that I have that spinning. Okay, so the shell method would have us take a slice this way, and we're looking at something like that. And again, if I take this and I roll it out, this one shell, imagine it like that Campbell soup label that I was talking about a second ago, or Progresso, if you like that better, it doesn't matter. Okay, so this radius is actually the y value. Okay, so that radius is the y value. And so this distance is going to be 2 pi r, the radius, so 2 pi y. Now this distance is the height. Well, I have everything turned sideways here, so because the idea is I'm cutting this and I'm unrolling it. Okay, I'm peeling it. Okay, so this height turned sideways is whatever this change in x is. Well, really what that is this is all starting at 2. This is x, so this is 2 minus x. Now, if that bothers you, then stop the video for a second and go back and figure out what that is. Okay, make sense out of it. 2 minus x is that distance. Okay, x is the distance from the y-axis to the point. If this is 2, sorry, this is 4. Ooh, Sanford caught himself before he got done. Thank you, thank you, thank you. Okay, so that's really a 4 minus x. Okay, so thank you for those watching at home yelling, Mr. Sanford, that's 4 minus x. Whew. All right, and then so this particular area then is going to be circumference times height, which is again sideways. And then to get volume out of this, I have to do thickness. Okay, so now thickness in this case, I should have gone up a little bit higher. Thickness in this case is actually going to be the thickness of that shell, and that's actually dy. Okay, and then we're going to add all of those up, and since this is about y, these are supposed to be about y. That's why I kept thinking 2, from 0 to 2. And the only problem in this is that this is not about y, that's x. Well, if y equals the square root of x, then x would have to equal y squared. Okay, so this really is going to be, okay, I'm going to rewrite it one more time. 2 pi y, 4 minus y squared, dy. Okay, that is the setup, and that's the part I'm most concerned about, is the setup. So again, the whole idea here is that I have this cylindrical shell. It's like, again, the wrapper off of a can that I slice it, and as I unroll it, it just becomes this rectangle, and it has thickness that we're going to add up. Okay. All right, what I'm going to do is take just a second, and I'm going to work this out, not during the recording, just so you can kind of see how it would go. But the biggest issue I'm concerned about is the setup, and then I'll let you just kind of see how this would shake out at the end. For those of you who would like to see how this played out, this is, I just went ahead and paused and then did the work here. Okay, so a little bit of cleanup. I pulled the 2 pi out, distributed the y, antiderivative, and then substituted the 2 and the 0. And so we end up with 8 pi cubic units. Now, for those of you who are just looking to see, now you might think this is harder method than the other one, and maybe it is, but there are some problems that this is easier. Okay, so I'm going to pop back to the previous one. This is us doing the same exact problem yesterday with a very different method, and again, we got 8 pi. So just so you know, you should come out with the same answer regardless of which method you use. And sometimes it'll just be a matter of you can choose which method you want to do, and other times not. Okay, so let's do another one. Okay, this is us doing the disk method, going around the y-axis with, again, y equals square root of x, and we're going to do the same exact problem again using the shell method. Okay, so again, we're going around the y-axis. We're taking the same curve, and this is that point 4, 2. Okay, and this time we're going to spin around the y-axis. Remember, the idea is this is an axis, and as it spins, this is attached to it, so it's going to spin around and make a circular shape here, and it looks like a reflection on the other side. And then we got a bunch of circles here. Okay, now again, I don't know if it's just this particular graph, but the shells on this, if we were going to do shells, and that's the point of this, is to get practice doing the shells, they're gonna look like this. No, actually, I'm wrong. Okay, and again, let me just pop back and see which one I did yesterday. Oh, yep, that's right. Okay, so because this could be interpreted a different way, and I think I mentioned that on the last video, we could have interpreted it as meaning this bottom region between the x-axis and that, and so that would actually be a better one for doing shells than the one we're about to do. But I want to do the same problem that we did yesterday. Okay, so again, the idea here is I'm going to take that little circle-y thing and unroll it. Okay, so this distance is the circumference around there, and circumference is 2 pi r, and the radius in this case is the x value. And the thickness of each shell will be dx. Okay, so as we go 3D with this little guy, that thickness is going to be dx, and the circumference is going to be 2 pi x. Height-wise, again, similar to the last problem we just did, well, this height is y equals 4, and this height is y. And so the difference is the height of that shell, and it's going to be 4. Now see, I went and did it again. That's scary. Sorry about that. So this is y equals 2. Yep, see, I can read. So then this distance for the height of the shell will actually be 2 minus the y value. 2 minus y. Okay, and now we can go ahead and we know that y is going to be the square root of x, so I can call that 2 minus the square root of x. Okay, so as I set this up, the volume of one of these shells is the circumference of the shell, 2 pi x, times the height of the shell, 2 minus the square root of x, or 2 minus y, times the thickness, which is the dr, or the dx in this case, and then we're going to add them up from x value to x value, which is from 0 to 4. This is the volume. This is the setup. This is the big deal. This is the thing that's new. At this point, it's just a matter of doing an antiderivative. Okay, so I'm going to go ahead and do that. I'm going to, for you, it's going to take virtually no time. because I'm just going to pop back and you'll see it done. And in the meantime, so I'll be right back. Well, and I know that didn't seem like any time at all, but I'm back. So the idea here is I did antiderivative. The way I did it, I pulled the 2 pi out. I went ahead and distributed, and you can think about why this little guy is x to the 3/2. Just pause and think about it. Okay, and then similarly, you can think about why this is 2/5 right here after doing the antiderivative. And then I substitute the 4 and the 0 and do a little subtracting. And this is what I end up with for volume. Now, there were no units specified, so you don't have to do cubic units. I just want to make a big stink about the fact that that is actually volume. So 32 pi over 5 is what we got. Let's pop back to yesterday or the previous video, 32. Oh, I missed a pi in there somewhere. Ooh, Sanford. So that pi needed to come along. I guess I can fix that today. So there should have been a 32 pi over 5. So I missed that. Nobody brought it up in class, at least not this year. Okay, so that's it for the shell method on those 2 examples. And I think I'm going to look at maybe one more. And we're going to, again, revisit this problem. Again, same idea. And this time we're talking about rotating this bottom chunk around y equals 2, and this is going to be kind of like the very first example we did because it's well, actually more like the one we just did. All right, but we'll do that. Okay. All right, so let's do a little bit of drawing, and I know this is part of the issue. And so it says find the volume of a solid formed by rotating y equals the square root of x. Actually, I'm going to scooch it down a little bit. Sorry. So I have a little bit more room. Okay, so let's do something like this, and this will be, again, 4/2. Okay, and we're going to rotate this around y equals 3. So 1, 2, 3. Okay, so this is where the axle is, and what we did last time is we took this chunk, and again, there should be really some more wording here to clarify exactly what's what. Okay, and the idea is that this y equals 3 line is the axle. It's like somehow this is attached like a bike wheel with spokes or something like that, and it spins around that axle. And so up 3, this is 3 below the axis that we're rotating around. So this would have to be 3 above, and same idea here. This was horizontal, this is horizontal, and so there's like a little mirror image of this thing up here. And the whole idea is there's some spinning going on. Okay, and so if I grab one shell, one cylinder in the middle of all of this, okay, if I take that cylinder over here and I unroll it, it's a cylinder, a shell of a cylinder, everything is being measured from y equals 3. So this radius here is going to be actually 3 minus y. Because this, the distance from the x-axis up to the curve is the y value. So the radius is 3 minus y. So this circumference ends up being 2 times pi times r. And the thickness of this thing is dy. Okay, thickness or height is dy because it's measured vertically. Okay, and then this height is going to be, well, this number is actually x equals 4, and this distance is whatever x is, so the height is going to be 4 minus x. Now, you're already knowing that since so much of this is about, oh, sorry, that should be right here, 4 minus x. Since so much of this is about y, like especially the fact that the thickness is about y, the rest of it has to be about y. Okay, so if I do a little adding up, I'm going to go from a y value to a y value. And I'm not going all the way up to 6 because really I'm just talking about the curve. These are the y values of interest because the other half of this happens automatically, part of the circumference times height times whatever. Okay? Okay, so this is 2 pi times 3 minus y times 4 minus x. And we're doing that with respect to dy, okay, with respect to y. Okay, so again, this is the setup. You can think about why that's y squared, for what reason. This is the setup, and again, I'm going to magically pop in with everything done. All right, well, here's the wrap up for this one. So we already set it up. Again, it's 2 pi r times h times the thickness, which is dy. Pulling the 2 pi out and doing a little bit of foiling, and I'm kind of in backwards order because of that y squared at the end, so it ends up being y cubed at the end when it's y times y. Doing an antiderivative then, and then substituting, we end up with 24 pi cubic units. I didn't actually finish this problem last time, so I don't have an answer to compare it to. Now, a lot of times what's going to happen is there's going to be a judgment call. I think the 3 problems today were probably actually easier using disk method, but it's not bad seeing the shell method on problems that aren't as easy. Now, the other catch in here is sometimes there are going to be problems where what you end up doing is like the area between, or the volume between 2 curves. Like for instance, if I end up spinning something that looks like this around the y-axis, the cylinders would look something like this, and we'd be talking about, you know, maybe this is a y2, and maybe this is a y1, or vice versa, and this is an x. So you're going to be doing like 2 pi r times the height, and since this is a dx, we'd be saying dx, and you'd be adding them up from whatever this x value is to whatever this x value is. Okay, and I don't know what it is, but so sometimes this is totally the way to go, this shell method. Sometimes it actually is harder. It just depends on what kind of equations you're working with and what kind of other stuff you have. So again, be patient. Having a drawing is the key. Being able to picture what's going on, and I know this is not fun. Just again, be patient with yourself. All right, well, thanks for hanging with me. This is SanfordFlipMath, and we are through. Bye-bye.